Hello again, everybody. We are going through the paper one of your CAPS matric syllabus just before the exam. You want to make sure that you're able to answer all the questions. So I'm going to just show you the past 4 years papers, and then we will just have a look at how we do them, not actually do them. Let's have a look at question number 6. Doppler, lovely. So you should all score 100%. If you don't do so well in the work energy theorem, you should do well in the Doppler. So it says here, the siren of a train moving at a constant speed along a straight horizontal track emits sounds with a constant frequency. A detector placed next to the track records the frequency of the sound waves. The results obtained are shown on the graph below. You see there's a high frequency and there's a low frequency. Now, first of all, is the source, what is the source of the sound? It's the train. So is the train moving? Yes. So the source is moving. The listener is stationary. He's the detector placed next to the track. So the first thing we've established is that the source of the sound is moving. And look, there's a high frequency and a low frequency. So high frequency is when something is moved, when objects are moving together, the frequency is high. And when they're moving apart, so when the train passes the detector, there's the low frequency. So if we know there's only one big formula in Doppler. So this is going to be frequency of the, well, both of these are frequency of the listener, but this is when it's moving towards the detector, and then this is the frequency of the listener when it's moving away from the detector, but we do not know the frequency of the source. They don't tell us. Okay. State the Doppler effect in words. Okay, what is the Doppler effect in words? What is Doppler? It is the apparent change in frequency between a source of sound and a listener when they are moving relative to each other. So moving together or apart, it is the apparent, there's a word, not apparent, it's the word, yeah, I think it's apparent, change of frequency of sound of a source when it's moving relative to the listener. Hey, go and check out your definition. So the Doppler effect got in the words, there's an apparent or it's actually an actual change, apparent change of frequency when the source is moving relative to the listener. That sounds like I botched it, but go and check it up in the memo. Does the detector record the frequency of 3148 when the train moves towards or away? Towards, because it's always higher when it's towards. Calculate the speed of the train. Take the speed of sound in air as 340. So what you're going to do is you're going to get that formula for Doppler. Okay, let's just quickly have a look at that formula for Doppler. Where is it? Here. This formula. So there's the frequency that the listener hears, and you're going to substitute all these values in, and you're going to do it twice, right? One for when it's coming towards you, and one when it's going away from you. And you're going to make, and then you're going to find the FS, frequency of the source. Going to use two simultaneous equations, and you equate these two equations to find the frequency of the source. So that's the formula that you're going to use. Okay, and then you're going to use two simultaneous equations to find the speed of sound in air. We have a slight shortcut. I just want to write it on the board that helps us. So once you put the ... 1 and ... 2 for the two formulae, one with that value, one with that value, and they tell you that the speed, they must tell you the speed of sound in air there. They give it to you, it's 340. You remember? So let me just stop sharing for a moment here. Let's just go here and stop presenting. So you've got your formula. It's going to be frequency of the listener equals V plus minus V plus minus velocity of the listener over velocity of the source times frequency of the source. But don't forget, you're going to write this exactly as it is on the data sheet. Okay, there may not be brackets. I forget exactly word for word. Then when you substitute in what is the velocity of the listener? 0. So you're going to put your 0 there. There's your 340 plus minus 0, and then the velocity of the source, which is the moving train. If it's coming towards you, this is going to be plus on top, minus on the bottom. Remember, we said, you can remember, if things are moving towards each other, a towards is a plus on top, a minus on the bottom. So this would become plus, this would become minus. And for the other one, it would be minus on top, plus at the bottom. And then you would have the frequency of the listener is smaller, the smaller value there. Then you say, once you substitute in your values, you say 1, and the second formula you say 2. And then we have a formula that helps us to work out the velocity of the source. And this is the formula. If we take the frequency of the highest minus the frequency of the lowest times the speed of sound over the frequency of the highest plus the frequency of the lowest, we add those two, that gives us the velocity of the source or the listener. So this is just a shortcut method of finding the velocity of our source in this case. So after you've done 1 and 2, you can write that formula as you've changed the subject of the formula, and then you work out your answer. You get the velocity of the source. Okay, so let's go back and present again. Okay, so you don't get a mark for you just get marks up to saying 1 and 2 for the 2 formula, and then you get 1 mark for your final answer. All of that doesn't count anything. So you can write it or don't write it. It makes no difference. The detector started recording the frequency of the moving train siren when the train was 350 meters away. Calculate the time indicated on the graph above. So once you've worked out the speed of the train, and if you've got speed and you've got distance, you can work out time. Remember, velocity, once you worked out the velocity here, you got the velocity of the train. This formula comes in all the time. Velocity equals distance over time. So if you know the distance and you know the velocity, your third one is time. So V, velocity equals distance or displacement over time. They give you the displacement. So you put the 350 over the time equals whatever your answer was in 6.3. So that's easy. Let's just go to the previous year's Doppler question. The siren of a police car which is traveling at a constant speed along a straight horizontal road with sound waves. So this is again, velocity of the source is moving. Detector P placed inside the police car and detector Q placed next to the road at a certain distance away from the car. The two detectors record the changes in the air pressure reading caused by the sound waves emitted by the siren as a function of time. The graphs below were obtained from the thing. So here is the air pressure versus time recorded by the detector P in the car. So this must be the actual, this is the actual, if it's in the car, there's no Doppler effect. This is a detector on the side of the road. Now, do you see this wave? What have they given us here? They've given us air pressure over time. So one wave seems to take 18 times 10 to the 4 seconds. Okay, so don't forget, so that's the period of the wave. So here they give us the period of the wave. and we can work out the frequency of the wave by the inverse of it. There's the formulas on your data sheet. Here's the only way they can trick you in Doppler. They give you a period. How do you find the frequency? Frequency is 1 upon period, or period is 1 upon frequency. It's on your data sheet. And so from the period of the wave, you can work out the frequency. Same here. So you work out the two frequencies. Now you've got frequencies. This is the actual police car. This is next to the road. So look, this time is longer. So this is obviously when it's moving away, and this is when it's normal. This is the non-Doppler. This is when it's moving away. So what do they say here? Different patterns are shown above for the same sound wave emitted by the siren. What phenomenon is illustrated by the detector showing the different patterns? And it's Doppler. It says the police car is moving away from detector Q. Well, we knew that because the period is bigger. Use the graphs and give a reason why it can be confirmed that the police car is moving away from the detector. Well, we could say the period is longer, therefore the frequency is shorter, is less in the one that is moving away. And then they say to use the graphs and give a reason. So because the period is longer, the frequency is shorter, the inverse relationship between period and frequency. So because the period is longer, the frequency is shorter, and therefore that shows that because the frequency is less, it shows that it's moving away. Calculate the frequency of the sound waves recorded by detector P. So what are we going to do? We're going to go to the only formula in Doppler. Here's, you worked out the two, calculate the frequency of detector P. So what are we going to do? Frequency equals 1 upon period. And therefore, we're going to say 1 upon 18 times 10 to the minus 4 is going to give us our frequency, and that's how we're going to get our 3 marks. Use the information in the graphs to calculate the speed of the police car. Take the speed of sound in air as 340. So what are we going to do? We're going to go to our standard Doppler formula. We've got the one frequency here, 1 upon this period. That's going to be the frequency of the source. Here's the frequency of the listener. They've given us the speed as 340, and then we're going to calculate the speed by just plugging all those values in. Easy peasy. Let's have a look at 2018 Doppler. The alarm of a vehicle parked next to a straight horizontal road goes off, emitting sound waves of wavelength 0.34 meters. Okay, whenever you get a wavelength, you're going to turn it into a frequency. How are you going to do that? Velocity equals frequency times wavelength. They're going to give you, there's the velocity of speed of sound in air. That velocity equals frequency times this wavelength. A patrol car is moving at a constant speed on the same road. The driver of the patrol car hears a sound with a frequency 50 hertz lower. So whatever this frequency is, subtract 50, and then you're going to say that's the frequency of the listener. So it says the alarm of a vehicle parked next to a straight horizontal goes off, emitting sound. A patrol car is moving at a constant speed. So is the source going to be, is the source of the sound going to be moving or not? Well, the source is stationary. So the listener is moving in this case. The patrol car, it has a constant speed. So the patrol car hears, so the listener hears it as 50 below. So all you have to do is change these, understand the problem, and then convert and put them into the formula eventually. Let's say, state the Doppler effect in words. Okay, again, it's the apparent change in frequency when the source of a sound moves relative to the listener. Is the patrol car driving towards or away from the parked vehicle? Well, if the patrol car hears lower, it's moving away. Give a reason that due to the Doppler effect, the frequency drops when the listener is moving away from the source. Calculate the frequency of the sound alarm emitted by the alarm. Remember, that's just what we've done. We convert the wavelength into frequency by saying velocity, there's velocity 340 equals frequency times wavelength. So we calculate the frequency. Now the patrol car moves a distance of x meters in 10 seconds. Calculate the distance. There again, we've now worked out, it says here, the patrol car moves a distance of x meters. Calculate x. So we've got to work out the velocity of the listener. So we're going to work out the velocity of the listener by using our standard formula for Doppler, right? You know, it's the same one that's on the board behind me. Frequency of the listener equals V plus minus V listener over V plus minus V source. So you've got all the things you need to find out the velocity of the listener. Once you find out the velocity of the listener, it says he moves a distance of x meters in 10 seconds. So you say velocity equals distance over time. If you know the velocity, you can therefore work out what x is, or the distance. And that would give you your 1 or 2 marks at the end. So you first work out the velocity of the patrol car from your normal formula, plugging in 340 velocity of the listener is moving away, so it's going to be negative on top, positive at the bottom, negative on the top, positive at the bottom. The velocity of the source is going to be 0, and you're going to work out the velocity of the listener from this, because you've got your 2 frequencies, easy peasy, and then substitute, use the formula velocity equals distance over time, and solve for distance. Let's just have a look at 2017. Police car is moving at a constant velocity with its siren on. It passes a stationary listener. So here, the velocity of the source is going to be moving. The source is moving. The listener is stationary. Here's the frequency of the sound of the siren detected by the listener. There's a high, there's a low. So this is the siren as it's coming towards, there's as it's going away. State the Doppler effect in words. We've done that. Write down the frequency of the sound detected by the listener as the police car approaches. So you just look at the high value. As it approaches, it's 170. As it passes, it's 130. There's your 2 answers. Calculate the speed of the police car. Take the speed of sound in air to be 340. So like I said, you're going to create 2 simultaneous equations, one with this frequency, one with that frequency. You're going to say dot, 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 1, dot, 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 2. Don't forget you're going to have that your listener is stationary and that your source is moving. And then finally, you're just going to use that same formula that I said. You're going to use frequency high minus frequency low over frequency high plus frequency low times velocity. So equals the velocity of the source. So you're going to work out the velocity of the speed of the police car. So you're going to do 2 simultaneous equations for both frequencies, and then you're going to use the equation that I showed you on the board to work out the velocity of the police car in this case. Okay, great.